All right, this is going to be our walkthrough for the homework assignment titled Integral Practice. So we're just going to do a bunch of integrals. The first chunk of these are going to be indefinite integrals, and we'll have some definite integrals after that. So we'll start off with a nice easy one using the power rule. Right, the integral of x cubed plus 6x plus 1 dx. Well, we'll just go up to x to the fourth and divide by 4. And then we'll go up to x squared, and when we divide 6x squared by 2, we'll end up with 3x squared, and the 1 just becomes an x. And of course, don't forget your plus c. For our second one here, in order to do this integral, we're just going to want to distribute this out first to write it into a form that we can use the power rule. So 1 times 2 is just 2. And then negative t times 2 will be negative 2t. And 1 times t squared will be plus t squared. And negative t times t squared will be negative t cubed. So this is our new integral. It's the integral of 2 minus 2t plus t squared minus t cubed dt. And we'll just integrate each of those. So 2 will become 2t. Minus 2t squared will become a minus 2t squared over 2. Or just minus t squared. And then t squared will become t cubed over 3. And minus t cubed will become minus t to the fourth over 4. And of course, don't forget your constant at the end, plus a c. We'll need to use the same process here for this one. We'll just distribute out 2 minus root x squared. Right? If we need to do that off to the side, we can, right? 2 minus root x times 2 minus root x. Well, the 2 times the 2 is going to be 4. And then we'll have a minus 2 root x and another minus 2 root x, which will be minus 4 root x, or minus 4x to the 1/2. And then minus root x times minus root x should just be a plus x. And then our dx. And then we'll just integrate each of these. The 4 will become 4x. The 4x to the 1/2 will go up to x to the 3/2. And then we'll multiply by the reciprocal of that. We'll multiply by 2/3. So that's going to be a minus 8/3 x to the 3/2. And then we'll just do plus x squared over 2. And of course, don't forget the plus c at the end. For our next one here, we're going to need to rearrange the trig here. So we'll start off by recognizing that the denominator of this is just a rearrangement of the Pythagorean trig identity, right? So we're going to end up with sine x over cosine squared x dx, right? Because we know that sine squared x plus cosine squared x equals 1. So 1 minus sine squared ought to be cosine squared. And sine over cosine squared is the same as sine x over cosine x times 1 over cosine x. Well, 1 over cosine x is just secant. And sine x over cosine x is just tangent x. So really, we've just got the integral of secant x tangent x, which is one of our known integrals, right? The integral of that is just secant x plus our constant. Our next one here should be a fairly straightforward one. 3e to the u just integrates to become 3e to the u. And then secant squared is another known trig integral. That one's just tangent, right? Because the derivative of tangent is secant squared. So we have 3e to the u plus tangent u plus, of course, our constant. Our next one here, we'll want to do the distributing here first of the x into the 1 plus 2x to the fourth. So this is the same as the integral of x plus 2x to the fifth dx. And then now we'll just integrate that. So x should become x squared over 2. And then 2x to the fifth will go up to x to the sixth. And then we'll divide by 6. So 2 over 6 is just 1/3. So we'll have x squared over 2 plus x to the sixth over 3 plus c. Here's another fairly straightforward one, just a couple of known integrals. So 2e to the x should just integrate to be 2e to the x. And then cosine integrates to be sine, so 4 cosine should just be 4 sine x. And then, of course, plus our constant. The integral of x root x, we'll just want to rewrite that as x to the 3/2, right? Because it's x to the first times x to the 1/2, so that's just the integral of x to the 3/2 dx. Well, that goes up to be x to the 5/2, and then we'll multiply by the reciprocal, 2/5, so we get 2/5 x to the 5/2 plus c. Our next one here, again, fairly straightforward one, right? The integral of cosine is just sine. And the integral of sine is negative cosine. So if it's already got a negative in front of it, that'll make it a positive cosine, or positive 2 cosine x in this case, because we had the 2 in front of the sine. And then, of course, don't forget the plus c. For our next one here, we're going to want to do a term-by-term division here. We're first going to do y divided by y cubed. And anytime we have these rational functions where the denominator is just a singular term, a monomial, we usually just want to divide. So y over y cubed is 1 over y squared, or y to the negative 2. And then 5y to the 7th over y cubed is just 5y to the 4th. So now we're just integrating y to the negative 2 plus 5y to the 4th. And the integral of y to the negative 2, well, that goes up to be y to the negative 1. And then we'll divide by a negative 1, which would make that negative. And then 5y to the 4th will go up to y to the 5th. And then when we divide by 5, that 5 will just cancel out. And of course, don't forget the plus c. And if you want to rewrite that negative y to the negative 1 as negative 1 over y, right, this would be a perfectly acceptable answer as well. Either way is fine. All right, this is our first one here where we're going to do a U-substitution in these integrals. So we'll note that the thing inside of the square root is a good choice for u, because if I take its derivative, I get 4x plus 1, which is exactly what I have in my numerator. So we can see that that 4x plus 1 dx can just go away and turn into a du. So what we end up with here is an integral of 1 over the square root of u du. Well, that's the same as the integral of u to the negative 1/2 du, which we should be able to integrate, where we go up to u to the 1/2, and then we divide by the 1/2, which is just like multiplying by 2. So we have 2u to the 1/2 plus our constant. Right? And so, well, we need to rewrite this then as 2, and then our u was 2x squared plus x plus 1, plus, of course, our constant. For our next one here, we could do this one without a substitution, but then we'd have to distribute out 3x minus 2 to the 20th power, which I don't think we want to do. So we'll just u sub out the 3x minus 2, giving us du is 3 dx. So we should be able to just put a 3 inside this integral, as long as we put a 1/3 outside of it. And this will give us 1/3 of the integral of u to the 20th du, noting that our 3 and our dx turn into the du, and then the 3x minus 2 to the 20th becomes u to the 20th. So now we just integrate this. We end up with 1/3 of u to the 21st over 21 plus our constant, or u to the 21st over 63 plus some constant. Well, we then have to replace our u back with 3x minus 2 So our final answer should be 3x minus 2 to the 21st power divided by 63 plus some constant. All right, for this one, we are still going to want to substitute out that thing that's inside the parentheses, this time because we see that there's this x squared term here. And x squared is a portion of the derivative of x cubed plus 5, right? So if I let u equal x cubed plus 5, then du is 3x squared. And so if I can put a 3 inside of there, that will allow us to turn that dx and that 3x squared into the du. Now I can't just put that 3 in without canceling out with a 1/3 out in front. So now what we end up with is 1/3 of the integral of u to the 9th du, right? Noting that the 3x squared and the dx turn into the du. And then our x cubed plus 5 is just u, so it's u to the 9th. So we end up with 1/3 of u to the 10th over 10 plus some constant. And of course, that'll be 1/30th of u to the 10th plus a constant. And u was x cubed plus 5, so we might as well just replace that now. And there's our final answer. For our next one here, we'll again want to do a substitution for what's inside that square root, right? U will just be 4 minus t dt. Then du is just -1 dt. Well, it's easy enough to put a -1 inside of an integral as long as we put a negative outside the integral as well. Right, so here's my -√4 minus t dt, right? And just a negative in front is like having a -1. So now I can rewrite this as the opposite of the integral of u to the 1/2, right? Because root u would be u to the 1/2, and then the negative dt gets replaced with the du. And so as we integrate that, right, we should be able to integrate that. U to the 1/2 will just become 2/3 u to the 3/2 plus some constant. And of course, we'll bring that negative inside there. So we'll end up with -2/3 of our u, which was 4 minus t, to the power of 3/2 plus a constant. This one looks like it might be a little tricky to begin with, but if we just recognize the fact that the derivative of e to the x is e to the x, well, an extra constant in there doesn't really cause a problem. So we can just let u equal e to the x plus 1, and du is now just our entire numerator. It's e to the x dx. So now this just becomes an integral of du over u. Well, we know that du over u integrates to be natural log absolute value u plus a constant, or natural log absolute value of e to the x plus 1 plus a constant. And of course, this answer is fine, but it's kind of redundant to keep the absolute value on there because e to the x plus 1 is always positive anyway. So either of these answers would be acceptable, but I don't want you to just go straight from here to here. Right? I want to make it clear here that we're removing those absolute values for a reason, right? Because e to the x plus 1 is always positive, and so those absolute values are just redundant and unnecessary. You don't have to remove them. If you leave it with it on, that's great. But it's nice to at least recognize that. All right, our next one here. When we see something weird inside one of our integrals, like an inverse tangent, that we maybe don't know how to integrate, we might want to just look and see if the derivative of that is somewhere in our function, which it is, right? The derivative of inverse tangent is 1 over 1 plus x squared. So if we let u equal the inverse tangent of x, then du is 1 over 1 plus x squared dx, which we have both a u and a du in there, right? This just becomes an integral of u. And then the dx over 1 plus x squared is our du. So this integral is just u squared over 2, plus our constant, of course. And we'll replace the u with inverse tangent. So we'll have inverse tangent of x squared over 2 plus our constant. Now here we've got the natural log of x squared over x. And so we'll note that the natural log of x is a function within another function, right? It's being squared. So oftentimes that's what we want to let our u be. If we let u equal the natural log of x, then du is just 1 over x dx, which we do have inside of our integral already, right? There's our 1 over x dx. So this just becomes an integral of u squared du. And to integrate u squared, we just use the power rule, u cubed over 3 plus a constant. And u is natural log of x, so this is just the natural log of x cubed over 3 plus our constant. All right, for our next one here, oftentimes if we have like something inside that square root, like a 1 minus 4x squared, that when you take its derivative, you can find some form of that in our numerator. It's usually good to do that substitution. So we'll let u equal 1 minus 4x squared, and du will be negative 8x dx, which we don't have, but we almost have it. We have the x part of it, and it's easy enough to multiply by negative 8 inside of that integral, as long as I multiply by a negative 1/8 outside of the integral as well. So now this will turn into negative 1/8 of the integral of du over root u. Well, 1 over root u is just u to the negative 1/2. So this is negative 1/8 of the integral of u to the negative 1/2 du, which is negative 1/8 times, well, that integral go up to u to the 1/2, and then multiply by the reciprocal of 1/2, or 2, and add your constant. And negative 1/8 times 2 is going to be negative 1/4, so we end up with negative 1/4 of root u, or u to the 1/2, so we'll just say negative 1/4 of the square root of 1 minus 4x squared plus some constant. All right, our next one here, if you look at what's inside that cube root, its derivative is partially in the numerator. And so if we let u equal 1 plus z cubed, then du is 3z squared dz. And I've got a z squared, so all I have to do is multiply by a 3 on the inside of that integral and a 1/3 on the outside. So now we can rewrite this as 1/3 of the integral of, we're going to have du from our 3z squared dz, and then we have a cube root of u in the denominator, which is the same as u to the negative 1/3. So we're integrating u to the negative 1/3 du with that 1/3 out in front. So we have 1/3, and the integral of u to the negative 1/3, well, we'll go up to u to the 2/3, and then we will multiply by the reciprocal of that, which would be 3/2, and of course add our constant. Well, 1/3 of 3/2, that should just become 1/2. So we end up with 1/2 of u, which was 1 plus z cubed to the 2/3 power plus some constant. For our next one here, we have secant cubed x times tangent x. And so what we might note here is that this is the same thing as the integral of secant squared x times secant x tangent x. And the reason we might want to do that is because then we can see that we could rewrite this using a substitution where u is equal to secant x, because then du would be secant x tangent x dx. And now we have the secant x tangent x dx. And we don't have just secant, we have secant squared. Well, that's okay. That just means we have the integral of u squared du. And if we integrate that, we end up with u cubed over 3 plus a constant, which is secant cubed of x over 3 plus a constant. All right, this one's going to be kind of similar. We got sine cubed of theta times cosine of theta. Well, we know that the derivative of sine is cosine. So if we just let u equal sine theta, then du can be cosine theta d theta. And if we do that, well, we replace the sine with u, so this becomes an integral of u cubed. And then the cosine theta d theta is just du. So we're just integrating u cubed du, which would be u to the 4th over 4 plus a constant. And just replace the u with sine. It's now sine to the 4th of theta over 4 plus that constant. All right, this next one here gets a little bit more complicated. Right? So when we first look at this, we're tempted, as usual, to do a substitution where u is 3 plus x squared. And then du would be 2x dx. But if we look at this, we might think that there's a problem, right? We don't have an x dx, we have an x cubed dx. And the 2 is easy enough to put in there. And in fact, let's put that 2 in there. So we could rewrite this as 1/2 out in front with a 2 inside of there, and then a root 3 plus x squared, and then an x and an x squared dx. And so if I do that, we can see that we have our 2x dx, right? That's what gives us the du. And we have root 3 plus x squared, which will just be root u. But we're left with this extra x squared term. Well, that extra x squared term is actually easy to deal with, right? If we just subtract 3, we get x squared is equal to u minus 3. So now we can rewrite this entire expression in terms of u. We have 1/2 of the integral of root u, which is just u to the 1/2, and then the x squared is u minus 3, and then the 2x dx is our du. Now we just have to distribute this through. We have 1/2 of the integral of u to the 3/2 minus 3u to the 1/2 du. And now we can integrate. We have 1/2. The integral of u to the 3/2 should be 2/5 u to the 5/2. And the integral of minus 3u to the 1/2, well, that'll go up to be u to the 3/2. And then we'll divide by 3/2, so we'll multiply by 2/3, which is just going to make that a minus 2 there. So we'll have minus 2 u to the 3/2 plus, of course, our constant. Now we'll distribute our 1/2 through, and we'll replace all the u's with 3 plus x squared. So don't go through all this effort and forget to replace the u's. You always have to replace them. So 1/2 of 2/5 is 1/5, and u was 3 plus x squared, so we've got 3 plus x squared to the 5/2. And then 1/2 of 2 is just 1, so we just have minus our u, 3 plus x squared to the 3/2. And of course, don't forget to throw in your plus a constant here at the end, because if you go through all that effort and forget the plus a c, you'll probably be pretty annoyed. All right, for this one, we have x root x minus 1. So there's a couple ways to go about this one, and I think probably the easiest way is to just do a real quick substitution where u is equal to x minus 1. Then du is just dx, which is great, and x is equal to u plus 1. And what this does is it allows us to rewrite this so that we have u plus 1 times root u du. And now I can distribute this square root of u into these two terms, whereas before I couldn't distribute that x into the inside of that square root. So this is going to allow us to do this distributing. U times root u, that's u to the first times u to the 1/2, so that'll be u to the 3/2, and then plus u to the 1/2 du. Well, now we just integrate. U to the 3/2 should become 2/5 u to the 5/2, and u to the 1/2 should become 2/3 u to the 3/2, and of course, don't forget the plus c. We'll replace all the u's with what u was, which was x minus 1. So we have 2/5 of x minus 1 to the 5/2 plus 2/3 of x minus 1 to the 3/2 plus our constant. All right, here we have x over the 4th root of x plus 2. And so we'll just do kind of what we've been doing before, is we'll do this u substitution for the thing inside the root in the denominator. Nicely enough, this gives us just du is dx. But we are going to have an x to deal with. So let's note that x is equal to u minus 2. So we can rewrite this as the integral of u minus 2 over u to the 1/4 du. Right? And then now we'll do a term-by-term division here, giving us an integral of u to the first over u to the 1/4 should be u to the 3/4. And -2 over u to the 1/4 should be -2 u to the -1/4. Now we can integrate. U to the 3/4 will go up to be u to the 7/4, and we'll divide by 7/4 or multiply by 4/7. And then minus 2u to the -1/4, well, we'll go up to u to the 3/4, and we'll divide by 3/4, which is the same as multiplying by 4/3, which would be a minus 8/3 u to the 3/4, plus, of course, our constant. We'll now replace all the u's with x plus 2, and we've got 4/7 of x plus 2 to the 7/4 minus 8/3 of x plus 2 to the 3/4 plus our constant. All right, for our next one here, we're going to just go about that same process we've been doing. We're going to let u be that term that's in the denominator, inside the root in our denominator. So u is 1 minus x. Du will be -1 dx. And if we rearrange u equals 1 minus x, we should see that that means that x is equal to 1 minus u. And so we will integrate. Now our x squared will be 1 minus u squared. And then the denominator there is going to be root u. And then we forgot our dx there, but that du should be a dx. If we should be able to turn that dx into a du if we put a negative on the inside and also a negative on the outside, right? So I should have done that before. So we still have the negative inside, the negative outside, and then that negative and that dx will turn into our du. So our numerator will end up distributing out to be 1 minus 2u plus u squared Now we have a du there over u to the 1/2. And so now we can do, again, our term by term division here. And as we do this, I'm just going to throw that negative sign inside of the integral because it doesn't really make things any more difficult to have it inside. So 1 over u to the 1/2 is u to the negative 1/2. And if we throw that negative in, we got negative u to the negative 1/2. And then the minus 2u over u to the 1/2 should just become a positive 2u to the 1/2. And then the u squared over u to the 1/2 is u to the 3/2. So we'll have minus u to the 3/2 du. We'll integrate all of this. U to the negative 1/2 will go up to be u to the positive 1/2. And then we'll multiply by 2. So we'll have negative 2 u to the 1/2, or negative 2 root u. And then we'll go up to u to the 3/2, and we'll divide by 3/2, so multiply by 2/3, which will be 4/3. And then we will go up to u to the 5/2 and divide by 5/2, which will be multiplying by 2/5. Plus, of course, our constant. And don't forget to replace all of the u's with 1 minus x. And even if you run out of room almost, don't forget the plus c at the very end. All right, this is our last of our indefinite integrals here. And then we'll move on to doing a few definite integrals. So we'll start off this one the same way as the last ones. We'll let u equal x cubed plus 1. Du will be 3x squared dx. And when we rewrite this, we'll note that we don't really have 3x squared in there, but we can put a 1/3 out front and a 3 inside. And then x to the 5th can be rewritten as x squared times x cubed. And then we'll still have that root x cubed plus 1 dx. And so now 3x squared dx can become du. Root x cubed plus 1 can become root u. And x cubed, well, x cubed is equal to u minus 1. So x cubed can become u minus 1. So we end up with 1/3 the integral of u minus 1 times u to the 1/2 du. And now we can just distribute that together. We have 1/3 of the integral of u to the 3/2 minus u to the 1/2 du. And we have 1/3 of 2/5 u to the 5/2 using the power rule, minus 2/3 u to the 3/2, again using the power rule plus some constant. And now we'll distribute that 1/3 through everything. So we end up with 2/15 of u to the 5/2, and we'll rewrite u as x cubed plus 1. Don't forget to do that. And then minus 2/9 of x cubed plus 1 to the 3/2 plus some constant. And that is our final answer there for our last indefinite integral. And so now we'll go through and we'll do some definite integrals here. So starting off with just a nice power rule definite integral. So we'll just integrate this. 6x squared will go up to become x cubed. And when we divide by 3, we'll get 2x cubed. And then the minus 4x squared will become a minus x squared. All right, we'll divide the 4 by 2, which will be minus 2x squared. And then the plus 5 will become a plus 5x. We're going to evaluate from 0 to 2, which is really convenient for this particular problem, because when I put in 0 to all of these, I just get 0. And be careful about that, though. Not always will you get 0 when you plug in 0 to the function. right? Not all functions equal 0 when x is 0, right? Polynomial functions that don't have a constant will, but if you have a cosine in there or an e to the x in there or any number of other things, it doesn't necessarily equal 0. So make sure you check that. Don't just assume that when the lower limit is 0, the second part of this is going to be 0. That's not always the case. And so, well, 2 times 2 cubed is 2 cubed is 8, and 2 times 8 is 16. And then we have 16 minus 8 plus 10, which comes out to be 18. All right, for our next one here, we're again just going to use the power rule. So 5y to the 4th, that goes up to y to the 5th, and we divide 5 by 5, so that's just 1y to the 5th. And then the 6y squared will go up to be y cubed, and when we divide the 6 by 3, we get minus 2y cubed, and then plus 14y. And we'll evaluate this from negative 3 to 0. So first, when we plug in 0 to all of these, each of those terms will be 0, so we just get 0 for that. And then we'll subtract a negative 3 to the 5th minus 2 times negative 3 cubed plus 14 times negative 3. And when we do that arithmetic, right, negative, we have a negative out in front, right? And negative 3 to the 5th power is going to be negative 243. And then negative 3 cubed is negative 27. And so negative 27 times negative 2 is going to be a positive 54. And then negative 3 times 14 is just going to be a negative 42. If we flip the signs on all those, it's just 243 minus 54 plus 52. So really that's just 243 minus 12, which is 231. All right, for this next one here, we're going to do the integral from negative 2 to 2 of 3u plus 1 squared. And now you could do a substitution on this, or you could just distribute it out. I think I'll just distribute it out. So that's 9u squared plus 6u plus 1 when you distribute it. And then when you integrate it, 9u squared will become 9u cubed over 3, or 3u cubed. And then the next term there should become just 6u squared over 2, which will just be plus 3u squared, and then plus u. And we'll evaluate from negative 2 to 2. And so we'll first plug in 2. So we have 3 times 2 cubed, that's 3 times 8, plus 3 times 2 squared, that's 3 times 4, plus 2. And then we'll subtract from that 3 times negative 2 cubed, which is negative 8, plus 3 times negative 2 squared, which is 4, and then minus 2. And if we put all that together, right, we're going to have a 12 here that's going to cancel out with this 12 that we're subtracting. And then we're going to have a 24 here that's going to add to another 24 because it's minus a negative 24. So that's positive 48. Plus 2 is 50. And then minus negative 2 would be adding another 2. So 50 plus 2 is just 52. All right, for our next one here, we've got the integral from 0 to 9 of root 2t. And we've got two options here. One is to just separate that as a root 2 and a root t, and then integrate it just using the power rule. The other is we could do a U-substitution for 2t. I think I'm just gonna rewrite this as an integral from 0 to 9 of root 2 times root t dt. And then that root 2 can just come out into the front of the integral, and I don't even have to really worry about it. And I'm just integrating t to the 1/2 dt. So I have root 2 times the integral of t to the 1/2, which is 2/3 u to the 3/2, from 0 to 9, or just root 2 times, well, we'll plug in 9 to that. The 9 to the 3/2 will square root the 9 first to get 3, then we'll cube it to get 27. And then if I do 0 to the 3/2, that's 0, and times 2/3 is still 0. So we end up with root 2 times 18. Well, that's just 18 root 2. All right, our next one here, we have 1 plus the cube root of x over the square root of x from 1 to 64. Well, this looks like one of those ones where it's best to simplify by dividing first. So let's just rewrite this as an integral from 1 to 64 of 1 over root x, which is x to the negative 1/2, and then the cube root of x over the square root of x. Right? That's x to the 1/3 over x to the 1/2. Well, that means I need to subtract the exponents. And 1/3 minus 1/2, if we get a common denominator there, that's 2/6 minus 3/6, which would be negative 1/6. So that's x to the negative 1/6. So x to the negative 1/2 plus x to the negative 1/6 dx. Now we'll just integrate. The integral of x to the negative 1/2, that goes up to be x to the 1/2. And then we multiply by 2, because that's the reciprocal of 1/2. And then the x to the negative 1/6 will go up to be x to the 5/6. And then we'll divide by 5/6 or multiply by 6/5. And so now we'll evaluate that from 1 to 64. And so as we do that, we have 2 times the 64 to the 1/2. Well, that's the square root of 64, which is 8. And then plus 6/5 of x to the 5/6. Well, the sixth root of 64 is 2. And then if we do 2 to the 5th, that's 32. So we have 32 times 6/5. And then we'll subtract from that all of this evaluated at 1. Well, the square root of 1 is 1, so 2 times 1 is 1. And then the 1 to the 5/6 power is still just 1. And so we'll just add to that 6/5. So we'll do some arithmetic here. We've got 16 and a minus 2. That's 14. And then we've got 32 times 6 is 192. So we have plus 192/5 minus 6/5. Well, 14 should be 70/5. So if we do 70/5 plus 192/5, that ought to be 262/5 minus 6/5 ought to be 256 over 5. All right, here's a nice easy integral. That's just a function we should be able to just integrate right off the bat. The integral of secant tangent is just secant theta. So this is just secant theta from pi over 4 to pi over 3. Well, that's the secant of pi over 3 minus the secant of pi over 4. The secant of pi over 3, right, well, that's 1 over the cosine, right? The cosine of pi over 3 is a half, so the secant of pi over 3 is that reciprocal. That's just 2. And then the secant of pi over 4, well, the cosine of pi over 4, right, is root 2 over 2. Or so if we take the reciprocal of that, the secant of pi over 4 should be 2 over root 2. Well, that's really just the same as root 2, right? Because that's 2 to the 1st over 2 to the 1/2, which should be 2 to the 1/2. So we get 2 minus root 2. All right, our next one here, we're going to do a quick U-substitution on the 4 plus 3x portion. So we'll let u equal 4 plus 3x, which means that du is 3 dx, which means we're going to have to put a 3 inside and a 1/3 outside. And in fact, I'll just kind of sneak that in here, a 3 here and a 1/3 here. And then we're going to have to change our limits of integration also, right? Because when x is 0, u is actually equal to 4, right? If you plug in 0 here. And when x is 7, u is equal to 4 plus 3 times 7. 3 times 7 is 21, so that'll be 25. So this can be rewritten as 1/3 of the integral of u to the 1/2 du, and we'll go from 7 to 25. Sorry, not 7 to 25, 4 to 25. Our new lower limit was 4, not 7. So we're going from 4 to 25. And so now we'll just integrate. We have 1/3, and the integral of u to the 1/2 is just 2/3 u to the 3/2. And again, we're going to do that from 4 to 25. So really, this is like 2/9 of 25 to the 3/2 minus 4 to the 3/2. So 25 to the 3/2, if we square root the 25 first, that's 5, and then cube it is 125. And do the same with the 4. Square root it first is 2, and then cube it is 8. So we have 2/9 of 125 minus 8. 125 minus 8 is 117, and 117 divided by 9, what is 117 divided by 9? That comes out to be 13. So we end up with 2 times 13, which is just 26. Right, for this one we have sine theta over cosine squared theta, d theta, from 0 to pi over 3. Now we could do a U-substitution here, but it might be nice to just be a little more clever. This is 0 to pi over 3 of 1 over cosine theta times sine theta over cosine theta. Well, that does not look like cosine theta, but that's fine. Cosine theta, d theta, right? We have the sine over the cosine, and we have the 1 over the cosine. That takes care of the cosine squared in the denominator and the sine in the numerator, which of course is just the same as secant theta tangent theta, d theta. So a nice easy integral again. This is just secant theta from 0 to pi over 3. Well, we already figured out what the secant of pi over 3 was a little bit ago, right? Cosine of pi over 3 is 1/2. So the secant should be the reciprocal, which is 2. And the cosine of 0 is 1, and its reciprocal for secant should also be 1. So this is just 2 minus 1, which is 1. All right, for our next one here, we're looking at x squared root x plus 3. We'll do the same kind of process we've been doing, which is we'll let u equal x plus 3. And then that means that du will just be dx, which is kind of nice. But we are going to have to replace this x squared with something. So we'll note that x is equal to u minus 3. And we're also going to have to replace our limits of integration. So when x is -2, u should be -2 plus 3, right? We'll plug it in here, right? Which is 1. And when x is 1, u should be 1 plus 3, should be 4. So we should be able to rewrite this as an integral of x squared, which was u minus 3, so u minus 3 squared, times root u du from 1 to 4. And the nice thing about definite integrals is we don't actually have to convert back to terms of x because we convert those limits of integration. Now we're still going to have to distribute all this fun stuff out here. So u minus 3 squared is u squared minus 6u plus 9. And so we're going to have to multiply that by u to the 1/2, which is going to now give us an integral from 1 to 4 of u to the 5/2 minus u to the 3/2 plus 9u to the 1/2. But now we can integrate to get 2/7 u to the 7/2. And then this will become minus 12/5 u to the 5/2. And then plus, it becomes plus u to the 3/2 divided by 3/2, which is multiplying by 2/3. Well, 2/3 of 9 is 6. So that's plus 6 u to the 3/2. And all evaluated from 1 to 4. So now we'll just do the arithmetic on that, which is going to be a little annoying maybe. But 4 to the 7/2, first we square root the 4 to get 2, right? And then when we put in 2 to the 7th, what is that? That's 2, 4, 8, 16, 32, 64, 128, right? So we have 2/7 of 128 minus 12/5, and then we'll do 2 to the 5th power. So that's 32, and then plus 6 times 2 cubed, so 6 times 8. And then we're going to subtract from that 1, or all of these things evaluated at 1. So that would be 2/7 minus 12/5 plus 6. And when we put all of those together, I'm not going to go through all the arithmetic. You'll need to get a common denominator of 35. And so, you go through all the arithmetic and you end up simplifying it down to get 136 over 35. All right, for our next one here, we're just, again, going to use kind of the same process. We're going to have u is equal to 1 plus 2x. And du will just be 2 dx. So we'll throw in a 2 and a 1/2. And we'll note that when x is 0, u is 1. And when x is 13, u is 27. I just plug 13 into 1 plus 2x. And now we can rewrite this, noting that in the denominator here we have 1 plus 2x. Oops. We have 1 plus 2x to the 2/3 power, which is really just like 1 plus 2x to the negative 2/3, right? So we have 1/2 now of the integral from 1 to 27 of u, the 1 plus 2x, to the negative 2/3 du. And so we'll integrate that. U to the negative 2/3 should go up to be u to the 1/3. And then we'll divide by 1/3, which would be like multiplying by 3. So effectively, we've got 3/2 times the cube root of u, or u to the 1/3. And we'll evaluate that from 1 to 27, which is 3/2 of the cube root of 27, which is just 3, minus the cube root of 1, which is just 1, and 3 minus 1 is 2, and 3/2 times 2 is just 3. All right, we've just got a couple more of these here to go. So we've got the integral from 1/6 to 1/2 of cosecant pi t cotangent pi t. Now we should note that the integral of cosecant cotangent is negative cosecant, but we got to deal with those pi t's. So let's let u equal pi t, and du will be pi dt. Now that means we're going to need to multiply by a pi inside and a 1 over pi outside. So we're going to have 1 over pi times the integral from 1/6 to 1/2 of pi cosecant pi t cotangent pi t dt. And now we can rewrite all of this in terms of u, as long as we recognize that when x is 1/6, u is pi over 6, and that when x is, what's the other one, 1/2, then u is pi over 2. And so now we can rewrite our integral as 1 over pi times the integral from pi over 6 to pi over 2 of just cosecant u cotangent u du, right? And that pi with the dt turns into our du. So now this becomes negative 1 over pi, or we'll just put 1 over pi, times negative cosecant u from pi over 6 to pi over 2. Well, that's 1 over pi. And then we'll do negative cosecant of pi over 2. Well, cosecant is the reciprocal of sine, right? And sine at pi over 2 is 1. So the reciprocal of 1 is just 1. And since we have a negative there, it'll be negative 1. And then it'll be minus. And then again, we're going to have the negative there. And then the sine of pi over 6 is a half. And so the reciprocal of a half should just be 2. So now if we undo all of this, inside the brackets, we have negative 1 plus 2, which is just 1. We'll multiply it by 1 over pi and get our final answer of 1 over pi. All right, and this will be our last problem here for this assignment. It's another u sub question here, where we're going to let u equal what's inside that radical. So u is x squared plus 1. Du will be 2x dx. And we'll note that when we put in the 2 here and the 1/2, right, this is going to look like an integral from 0 to root 3 of 2x times x to the 4th times the root x squared plus 1. Well, x to the 4th, we should note, is the same thing as x squared squared. And the reason we want to do that is because from here, we can see that x squared is equal to u minus 1. And so I can replace that x squared with u minus 1, and then I'll square it. And of course, since it's a definite integral, we're going to have to replace our limits of integration. So when x is equal to 0, u is equal to 1. And when x is equal to root 3, our original upper limit, then u is equal to root 3 squared plus 1, or 3 plus 1, which would be 4. So our whole new integral now is going to become 1/2 of the integral from 1 to 4. Our 2x dx will become our du. Our x squared squared will become u minus 1 squared. And then we have our root u. Or 1/2 the integral from 1 to 4 of u squared minus 2u plus 1 times u to the 1/2 du. Or 1/2 the integral from 1 to 4 of u to the 5/2 minus 2u to the 3/2 plus u to the 1/2 du. And now we can just go ahead and do all of the integration there. If you want to throw the 1/2 inside, you can. If you don't want to, that's fine too. I think I probably would, but since I didn't write it inside there, I'm not going to. So we have a 1/2 out in front, and now our integral, which is u to the 5/2 there, becomes 2/7 u to the 7/2. And then the minus 2u to the 3/2 is going to become a minus 4/5 u to the 5/2. And our u to the 1/2 will become a plus 2/3 u to the 3/2. And again, we're evaluating from 1 to 4. Well, now I'll distribute this 1/2 through everything as I start to do this. So we end up with 1/7 inside of there. And then u to the 7/2, right? We've done that a few times today. The square root of 4 is 2, and then 2 to the 7th is 128. So 128 times 1/7 is 128 over 7. And then when we plug in the 4 to the, it's now going to be a 2/5 u to the 5/2. So that's going to be 2/5, so we'll put a minus sign. It's 2/5 of 2 to the 5th, and then 2 to the 5th is 32. So if we multiply that by 2/5, that's 64/5. And then when we plug in the 4 to the last piece there, which is now a 1/3 u to the 3/2, it's just 1/3 of 8, so plus 8/3. And then we'll subtract, of course, when we plug in 1, it's just going to be a 1/7, a minus 2/5, and a plus 1/3. And if you do all the arithmetic on that right here, you're going to get 127/7, and you're going to get a negative 62/5, and you're going to get a 7/3. You'll get a common denominator of 7 times 5 times 3, which is 105. I'm not going to go through all the arithmetic on it because it's kind of a pain, and you should be able to do the arithmetic. It comes out to be 848 over 105. And that is our final answer, and that is the end of our walkthrough for the integral practice homework assignment.